Hello, my name is Dr. Josu. I come from the engineering faculty of the University of the Basque Country. In this session, I'm going to introduce you our hardware proposal for SHM in airborne vehicles. The system was developed in collaboration with Ernova. The integrity of structures can be assessed during its life cycle, that is, the manufacturing of a structure, its installation, and during operation. There are two sets of techniques for the assessment of the integrity: the non-destructive testing (NDT) techniques and the structural health monitoring (SHM) techniques. The first ones, NDT techniques, are applied in the beginning of the life cycle of structures, that is, when they are manufactured and installed. The last ones, SHM techniques, are applied afterwards, during operation. We will focus on the SHM techniques, which increase the safety of structures and the service they provide. SHM also reduces the maintenance cost and extends the life cycle of structures. Out of all the SHM techniques available, we research on ultrasound guided wave techniques. Let's see in the following video how an ultrasound wave beam focuses into a specific direction thanks to the proper delay applied to the transducers in the array. The structural health monitoring ultrasound system, also known as SMUS, developed in our research laboratory, is named Pamela. It can acquire and emit simultaneously up to 18 channels. The weight of Pamela is 600 grams. It consumes 3 watts and its volume is smaller than 13 × 13 × 5 centimeters. Let's see now how the waveform of the electronic signals generated in Pamela is. These signals are applied to the set of transducers. The ultrasound signal generated is a tunable burst of about 300 kHz and 20 to 48 volts peak to peak. The generated burst can be windowed, for example using Hanning or Hamming windows. Moreover, Pamela can generate signals in phase or with an adjustable delay, which is useful to steer the beam of the propagated ultrasound wave. Let's see now the difference among the emitted and the received signals. When Pamela emits waveforms as the yellow one, it can receive a waveform like the green one. Here, for instance, when 40 volts peak-to-peak are emitted, only 110 millivolts peak-to-peak are received. The amplitude received is much smaller than the one generated. However, the waveform captured with SMUS is pretty much cleaner than the measurement with the oscilloscope. If we represent all the waveforms simultaneously acquired by Pamela, we can distinguish wavefronts reaching the receiver at different moments with different attenuations. As shown, there are a lot of samples acquired. Are all the samples transmitted to the computer or data processing node? It would take too long, so the answer is no. Pamela includes a preprocessing stage. The stage calculates the characteristic points of the waveform acquired. See the set of brown points. They are the maximum and minimum points above and below certain thresholds. If we try to reproduce the original waveform starting from the set of characteristic points, we see that the meaningful parts of the waveform are perfectly reproduced. In other words, we have a reduced set of data that defines the acquired waveform in similar terms as the original acquired signal does. The setup for the test consists of Pamela, the control software in the computer, the array of transducers, and the structure under test. Let's see now the performance demonstration of Pamela in a video hosted by my colleague Dr. Gil Garcia.
In order to run ultrasonic guided wave test, we need the following components. First off, we need something to test on. In this case, our unit under test will be a cross-ply composite laminate you can see here, where a 10 piezoelectric wafer active sensors have been installed. These sensors will be driven and read by a self-developed structural health monitoring ultrasonic system called Pamela. This system is capable to work with up to 18 sensors, but for the purpose of this demonstration, only 10 have been fitted. It's small and light and only needs a power supply and a USB connection in order to be controlled from a PC, where a monitoring software will be in charge of configuring and read back the measurements from the piezoelectric sensors. Well, the active mode can be helpful to run individual tests on a given specimen. Both the signal generation and the acquisition can be configured. Regarding the generation, along with the selection of the driven sensors, parameters like frequency, amplitude, up to 48 volts peak-to-peak, or number of cycles can be selected. The generated sine waves can be modified by applying different windows such as hand-in, ham-in, etc. On the acquisition configuration part, the selection of the sensors that will be read is carried out. The full waveform can be retrieved or only the characteristic points in the compressed mode. Finally, the type of test should be selected. It ranges from single, usual pitch and catch, round robin, where every generating sensor drives the unit under test sequentially and the acquiring sensors capture the incoming signals. Beamforming aims at focusing the energy on a given direction on a given angle. Finally, multiple signal delay applies arbitrary delays to any generated signals. We are going to carry out the single pitch and catch test. We can generate here, we can acquire here, single, and then we can start. Now it's complete, and here we can see part of the acquired waveform. In passive mode, only the acquisition is configured and no generation is performed. If an impact is detected, the structural health monitoring ultrasonic system, Pamela, captures the characteristic points and the passive mode is finished. Now I'm going to configure all channels. I will start monitoring the structure and I will hit it. Now a full active test should be run in order to quantify the received damage. Finally, the SHM mode deals with the detection of variations in the health of the structure over time by finding deviations from a pristine state. Firstly, we need to characterize the pristine state of a structure by running several times a given test. In this case, we have chosen a round-robin test with 10 generating sensors and the very same sensors acquiring the echoes. This means that each test generates 100 signals. Firstly, I need to create the structure, and now I can import the test. Here we can see the test, 10 generating sensors, the same acquiring the signals in a round-robin test. If I run this test 10 times, we will end up with 1000 set of characteristic points. Now I'm about to run the 10 tests to calculate the pristine state. That's it. Now I can run a single test. Each square represents how close to the pristine state that particular test was. The greener and closer to 1, the more similar it is. Now I will bend the specimen a little bit to increase its stress and will run the test again. Now it's not as green as before. I will try again harder and we will see the results. Finally, if I stop bending the composite specimen, the results obtained are like the ones obtained from the first test, as expected. The figure below represents the average of the values obtained in the 4 tests from the initial state through the 2 different stress levels back to the original position.
We have seen some simple and fast tests in the video, but Pamela can carry out tests that are more complex. For instance, we carried out fatigue tests in collaboration with Innova. The results are published in the first paper in the list. Further information about Pamela and its performance and capabilities can be found in the following scientific publications. They are all open access. Additionally, we would like to invite you and to your colleagues to contribute to the running special issue in Sensors Journal. It's called Structural Health Monitoring with Ultrasonic Guided Wave Sensors. So, to sum up and conclude the presentation, let me revise what has been introduced. there is a laboratory version of Pamela Smooth available with the features in the list. We have the potential and know-how to build an onboard version of Pamela. As a first approach, the features on the onboard version must be at least being small, lightweight and less than 1 watt power consumption. It must be able to build a sensor network as the one shown in the picture, for example 1 Pamela per substructure and all Pamelas interconnected to the avionics in the plane and eventually to the maintenance service. As well, passive mode or acoustic emission technique must be available for impact detection. The active mode or ultrasonic technique must be considered in the onboard version. And the final goal is to build a tool to monitor about 100 substructures in just a pair of minutes, in other words, fast as hell. Thank you for your attention and feel free to contact us for any questions you may have.